So in the last part of this introduction to the course, I'm going to talk briefly about different classes of inference problems. It turns out that classes of inference problems have names, and it's useful to know those names in order to enable us to talk about them. And then we're going to move through to some families of inference problems that we're going to cover in the course, and that will serve as an outline of the course. And I'll end up by just highlighting some of the textbooks that you might want to use to support your learning. So first of all, some sort of flavors of machine learning or flavors of inference problem. I'm going to talk about three sort of very broad classes or categories. Each one of them, machine learning system is going to experience a series of sensory inputs, and I'll call the sensory inputs X1, X2, X3, so on and so forth. In supervised learning problems, in addition to those inputs X, the machine is also given a set of desired outputs for those X's. So Y1 corresponding to X1 and Y2 corresponding to X2 and so on and so forth. And it's called supervised learning because the machine learning algorithm has a teacher which says for this particular input, you should be predicting this particular output Y. And the goal of that system is to take those training examples that comes from the supervisor or teacher, and then on a new input, we could call X star, predict some desired output Y star. Supervised learning is probably the most simple and most common type of machine learning problem. Unsupervised learning handles a harder problem. There are no labels here, there's no teacher or supervision signal, hence the term unsupervised learning. And the goal is, in the richest sense, to build a model of X. You just get X's, and in some sense you want to try and understand them, extract information from them, and that sort of information you gain by understanding it can then be used for decision making, prediction, communication, and so on and so forth. So there are lots of examples of this, but one example is a clustering algorithm. So a clustering algorithm seeks to put similar data points near each other and dissimilar data points further away from each other, and it aims to do that by just looking at the X's, so it gets no labels. You don't get to find out what cluster each data point is in. And clustering algorithms are used all over the place. So one example is for spam filtering. If you don't have labels for what is spam and what isn't spam from your email inbox, then you can use a clustering algorithm to identify clusters of similar emails and try and use that to extract a spam cluster, which can be used for automatic filtering. Labels help, but you can't expect to have all of your spam labeled. So that's unsupervised learning. There is a yet more general problem, which in the grandest version of it is called reinforcement learning. And in reinforcement learning, you get your X's, and the machine also has to produce actions at each step called A. So you see X1, you take action A1, you see X2, you take action A2, and so on and so forth. These actions then affect the state of the world, and you also receive along with them a reward, or depending on how pessimistic you are, a punishment, which comes after applying that action in the world. So after applying action A1, you get reward R1. After applying action A2, you get reward R2. And now the goal in this situation is to act in a way that maximizes rewards in the long term. This interfaces with Bayesian decision theory. The decision theory we just talked about was really valid for the static setting. So the decisions that we made are not going to affect the world, but this can be generalized to handle sort of full-blown sequential decision-making problem. We're not going to talk too much about reinforcement learning in this course, but we will talk about supervised learning and unsupervised learning. And future courses can build on this to introduce reinforcement learning. The foundations of the two are the same. Great. Okay, so that was about some flavors of machine learning. Let's look at the classes of problem that we're going to actually tackle in the course, and I'll go through these in order. And roughly speaking, they start off fairly simple with supervised machine learning and then progress to unsupervised machine learning at the end. So Miguel will be lecturing next week, and he'll talk about regression. And in regression problems, this is an example of supervised learning. So you get some X, Y pairs shown in the blue dots at the top left here. And the goal is, well, these blue things are data. And the goal is, if somebody comes along with a new X star, let's say here, X star, the goal is at that point to predict, what value Y would take, and maybe return to the user some error bars in that estimate. And the red line is showing sort of some kind of best fit through these points. So importantly in regression, the Y's are real valued quantities. And this has the name of regression. It shows up all over the place. One particular pertinent, fairly recent example is this example from Magic Pony here, who sold their company for 150 million US dollars to Twitter fairly recently, and included alumni from actually from the machine learning group. And they had a really neat idea, which was based on a regression problem, for turning low quality YouTube video, often live streamed, into nice high-res video on the user's laptop or phone as they were streaming it. And the idea worked as follows. They took nice high-res video to start with, and they passed it through the codec that's used by YouTube to produce sort of low quality but easy to stream video. And then the goal is, as a regression problem, this low quality video is our X's, our inputs. That's what's going to arrive on the user's phone or on the user's laptop. And the goal is to train a function, which is going to be a convolutional neural network, that acts on X and aims to recreate a really nice high-res video, or some estimate for it. So the high-res video we can call Y. They're going to be our gold standard. We'd like to convert a low quality rubbishy video frame into a nice high res original video frame Y. We won't be able to do that exactly, but the idea is once we pass it through this convolutional neural network, it'll output a Y hat, and we'll train the convolutional neural network so that the Y hat is as close to possible as to Y on the training example. On the training examples, and you can take a huge corpus of YouTube videos, high quality videos to start with, pass them through the codec. You have ground truth for lots of them, and you train the CNN to emulate that ground truth. So just tying this up to the picture, of course, these high-res video Ys are the blue dots essentially. The XY pairs here are the blue dots, and then this Y hat is the red line, best fit line shown on the left here. And that was the main piece of technology that Twitter was after when they acquired Magic Pony, so worth a lot of money. There are lots of other examples of regression problems. They're used, in many statistics applications. In political science, for instance, to predict polls. Multi-level regression models are extremely popular. In computer vision, you want to estimate the pose of an object in a scene. That's its three-dimensional configuration in the scene. That is, again, a regression problem from images X to pose variables Y. Weather forecasting, power demand forecasting, so on and so forth. I could talk forever about just regression problems. So Miguel will do that next week. The second type of problem that Miguel will cover is called classification. And that's exactly the same as a regression problem, except that the outputs are now discrete valued rather than real valued. So the outputs belong to one of k classes rather than to a real number. And so this again is an example of a supervised machine learning problem. Here's a particularly simple example shown at the top left here, where we've got two classes, and the blue dots indicate inputs X, which come from class 1. So all of these guys down here from class 1, and the magenta dots out here indicate things from class 0. And then the red line in between them is some line which we've come and fitted our machine learning model to obtain, and the machine learning model says everything above the red line is a 0 and everything below the red line is a class 1, and this is called a decision boundary for perhaps obvious reasons. That's sort of what we'd like sort of an idealized system to do. And there's lots of sort of applications for this technology too. Perhaps foremost amongst them, object recognition, where the x's here, the different dimensions in x, are an image, and the classes are these predicted tags. And I would encourage you to go and try out this website. This Clarify website is a really nice state-of-the-art, pretty much state-of-the-art computer vision system for performing object recognition that you can try out your own images on and have a play around with. And it's a pretty sophisticated thing to interact with. Speech recognition, similarly, face recognition, spam filtering, when you have labels, all falls into this sort of category of problem. Great, so that's classification. After that, we'll start to switch to unsupervised problems. And the first unsupervised problem we'll look at is called dimensionality reduction. And the basic idea behind dimensionality reduction is you have your x's coming in. The x's might be really high dimensional quantities. They might be images or data that you've recorded from multiple electrodes from the brain of a human. And what you'd like to do as an experimenter is to really summarize that information in just a few variables so that you can plot it, understand what's going on more easily, understand what factors are at play. And dimensionality reduction algorithms do just that. So they take big, high dimensional data and they project it down to a low dimensional space. So this is really useful for visualization. It's useful also because data often live near manifolds. So for instance, if you take an object in a scene, here I've just picked a sort of simple example, toy example of this digit 4, handwritten digit 4, and we imagine transforming that digit. So here we're going to transform it by rotating, but in a 3D scene, I might rotate my pen around or something like that. If I then look at how this affects all the pixels in the image of the 4, well, if I carry on rotating it, I'll get round back to where I started from. So in this high dimensional pixel space, if we look at the pixels of an image, by rotating the 4, we're tracing out a one-dimensional manifold, a line which is closed, comes back to where it starts from. So although the image is really high dimensional and the set of images corresponding to the 4 are really high dimensional, actually underlying it is a really simple one-dimensional manifold. And dimensionality reduction methods allow you to discover that manifold and to summarize the data using the position on the manifold, which is a much more parsimonious description. So that's one usage of them to model data which lives near a manifold. Another really common example for dimensionality reduction methods is just as a pre-processing step before you apply some other algorithm. So often you don't want to take huge high dimensional quantities and apply your sophisticated machine learning methods to them. You'd like to reduce them down to some small set of key features first, and then apply your sophisticated algorithms that take possibly a long time to run to those small low dimensional quantities, and therefore making them faster to deploy. So they're often a component of a much bigger machine learning pipeline, which is another good reason for covering them. So that's dimensionality reduction. The next set of problems we're going to look at is clustering. And I've already talked a little about clustering, the idea to group similar data points close to one another and disparate data points into different clusters. I've sort of shown that schematically in the top left-hand plot here. This kind of approach, as I said, is useful for spam filtering if you've not got labels for what's spam and what's not. It's also useful for things like image segmentation, where you maybe want to segment an image into foreground, background, objects, so on and so forth. You can do that in an unsupervised way without a user providing any labels at all using clustering. And I'll show some examples of that in our lectures. It can be used to cluster nodes on a social network. So individuals with similar interests or communities can be detected using clustering. There are lots of other examples, some of which are listed at the bottom here. Again, this is unsupervised. And then finally, in the last section of the course, we'll talk about sequence modeling. So modeling sequences using inferential techniques. There are lots of examples of this. Basically, anything you can think of is ultimately a time series, for instance, because things tend to change over time. But also things which aren't time series also correspond to sequences. For instance, the sequence of base pairs in a DNA chain or an RNA chain or a protein, that sequence is something we might want to model statistically. Handwriting recognition uses sequence models, modeling a financial time series like the FTSE, text modeling from natural language processing, video modeling from computer vision, modeling where earthquakes are likely to happen in a spatiotemporal way. All of these are sequence modeling problems, and there's an extremely rich set of technologies for handling these, which we'll start to dive into. Okay, that will be the last little bit of the course. In terms of textbooks that can help support your learning, there are 4 main textbooks. The textbooks go a lot further than the course and contain a lot more information. So I use them to support your learning rather than sort of working through these as a substitute for the course. The 4 major textbooks are listed here. I think all of them are available online at this stage.